Okay, so case study. So this week we've been looking at inference for our logistic regression. So we're going to go back to the beetles data set and see if we can do some of that inference. So let's head over. So here we've got our beetles data. Let's read it in. That seems to be working well. And just to remind you, what we did is we had different concentrations of this pesticide and we'd expose a certain number. So in the first experiment, we used 1.69. We had 59 beetles, of which 6 died. And we want to see the relationship between the probability of dying at different exposures. We had a bit of EDA, had a look at it. And then what we did is we created for each experiment the proportion that died. And then we did a plot to have a look at this, and we added a nice smooth. And so you can see as the concentration increases, we basically get an increase in the proportion that died. So the first model we're going to do is here we've got our successes and our failures. We've bound them together, and we're going to have a single predictor concentration. We've got our binomial with the logit all set up to go. And here is our output. So let's break it down. So first of all, here is our beta 0 and our beta 1. So our intercept and our slope in our link function. We can now test if these may be equal to 0. Usually the slope equal to 0 is the interesting one because it's asking the question, is there a relationship between probability of death and concentration? So this is the estimate. Here's the standard error. So this is the term we get from that Fisher information. We go to the Fisher information, we invert it, and then we look at the diagonal, and that's what that number is. We take this number, 34, minus 0, because that's what we're testing, divide by 2.98, and we get this Z value. Now, you know that as a rough rule of thumb, any Z or T values of less than minus 2 or greater than 2 are significant, but here we have it. You can see a very significant p-value. So you're pretty well using this almost the same way as you do linear regression. The main difference is now we have Z values because of the asymptotic normality of maximum likelihood estimators. We've got some other values here. We've got the null deviance and the residual deviance. Remember, the deviance is we're comparing the log likelihood of two models. Well, actually, it's 2 times the difference between them. But let's have a look at where these numbers come from. So what I'm going to do now to illustrate this is I'm going to create a model called M0, which is going to be the null model. What I mean by the null model is we don't have any predictors. All we have is an intercept. I'm also going to create what we call the saturated model. And remember, I said with the saturated model, basically, every experiment is going to get its own probability. So it's as over parameterized as we can get. For every single experiment, we're going to work out its individual probability of success. So completely saturated. And the easy way of doing that is I just treat concentration not as a numeric, but as a categorical. So there's my 2 models. So let's recap what we've got here. So we've got these 2 numbers. Now, first of all, the null deviance should be the difference, 2 times the difference between the saturated model and the null model. So this one is the saturated model, this is the null model. I've got the log likelihood of each model, and I go 2 times, and if we run that number, we get the 287, the 287. Degrees of freedom 8, degrees of freedom 7. So you notice there's a slight difference because this one is looking at the general null deviance. This is looking at the difference between these 2 models. That's all okay. This one now we're doing the saturated and the actual model we're looking at. And this gives us our, here, again, ignore the degrees of freedom. This is the one we care about. But the main thing we're interested in is this. The 14.514 equals the 14.514. So this here is the difference between the smallest model, the smallest model and the most complicated model you could have with this data. This one is looking at the difference between the really complicated model and this model itself. We can actually use this number to say, how good is our model doing? We know that this should have a chi-squared with 6 degrees of freedom. So you can do a quick calculation. I'll put it over here so we've got it. Let's go up here. I'm going to go 1 minus p chi-squared. Then I'm going to put in that value the 14.514, and the degrees of freedom will be 6. So what we're doing is saying we've got these deviance, and we're saying, is it significant? Is it just sort of almost noise, or is it there's a significant amount of deviance still there? And that's the thing we do. We're doing the 1 minus, and when we do that, we get a 0.024. So it's saying this model could somehow be improved. It's almost like you're looking at your residual sum of squares and saying, there's still a lot of variance in there we need to explain. And that's what we've seen here with this residual deviance. So you see that you can see that these things are created by log likelihood. And the most important one to us when we look at model is this one. And we can look and decide if that's still significant. And in our case, it is. So how do we improve the model? Well, let's have a look at our residuals. So we're going to go look at this one. We're not going to focus on these as much when we do logistic regression. But if we look at this, we seem to have a pattern. Notice these are high, then it goes low, then it goes high. It looks, I mean, there's not very many points, so it's hard, but it looks like there might be some curvature here. Yep. So let's deal with that. Let's add in a quadratic term. So the same thing before, we have the same response variable, success failures, concentration, but we've now got concentration squared as well. Now we look at our model. Okay, so now we've got this residual deviance. First of all, we notice that all our terms are significant. So concentration significant, and this extra term we've added in, our squared term, is also significant. So that's a good sign, it should be there. We can have a look at our residual deviance. Let's do the calculation. So it's 1 minus p chi-squared. The residual deviance, which is 4.3984. We've got degrees of freedom 5. And when I do this, now I get 0. So that residual deviance is not significant. That is, the stuff that's left over seems fine. We can also have a look at our plots. And can you see now that this is looking much more randomly scattered about that line? So it's looking pretty good. Some people use a normal QQ plot to sort of test if the model's looking quite well. You need group data, you need large enough numbers, but you can see these are roughly lying on the normal QQ. And it works on the idea that your residuals will be roughly normally distributed because you can use a normal approximation to a binomial. We can also compare these two models. So we've got these two models. The first thing we could do is an ANOVA test. And remember the ANOVA test, we're fitting the two models and we're looking at the likelihood ratio between them. So I've got my two models and I say I want to do a likelihood ratio test. Again, we've got a significant number there. We've got this 0.014. So we're saying there's a significant difference between these two models. And so we work on the principle with a significant difference, we keep the large model. If they're not different, if this was greater than 0.05, we go for the smaller model. So in this case, we definitely want a curved term. The other thing that we can do is we can look at AIC. We will cover this later in the course. But basically, it's a Kaike's information criterion. It's a measure of how good a model is, but it takes into account that it will penalise for models that are too large. So if we look at this, generally what you want is the smaller value, and you can see the smaller value is for model 3, and model 3 in this case is the one with the quadratic term. So next thing I'm going to do is I'm going to show you the different residuals. So you can get residuals using the residuals command, give it a model, and the types we normally look at in the district regression are either the Pearson or the deviance. Go to the lectures to remind yourself. So I've got the residuals for the first model with just concentration, and the second model with concentration squared as well, and we add those in. And now we can have a look at what they look like. So you can see here now I've put a smooth, you can see that curvature we saw in the first model that was a concern. If we do the deviance residual, same again, we see the curve. Now we go and look at the model with the quadratic term. Now it's settled down and settled down. So you can see the basic idea. You fit your model, you have a look of all your terms, your coefficients, significant, good. Look at the residuals. If that's still significant using that 1 minus p chi-squared, then you might want to see if you can improve your model somehow. How do you improve your model? In this case, we looked at the residuals and that helped us. So there you are. There is some logistic regression inference on the beetles example. See you next time.